Okay, let's go ahead and get started. Hope everybody's staying reasonably dry today. Yeah, unpleasant. Anyhow, what we're going to do to start off with is I'm going to ask each of you about your progress so far. So the goal here is not so much put you on the spot as it is where have you gotten so far, what insight have you gotten, and what ideas do you have that maybe other people in the class might experiment with. You don't necessarily have to restrict yourself to talking about stuff that actually works. You can also talk about general ideas. You know, this is a direction I'm thinking of going. I kind of want to do this, but I'm not sure how to code it. You know, stuff like that is all totally legit. So, start with you, Spencer.
Okay. So as for progress in the project, I'm about halfway finished. I haven't implemented alpha beta or anything after that, but I've done everything before.
Okay.
As for the evaluation method I want to implement for my own, I want to implement a very aggressive AI to where it evaluates based upon how many of its own checkers are on the opposite side of the board.
Oh, okay.
So it will prioritize getting them over there, possibly getting kings, and then defeating the opponent on their own side.
Okay, so going after them in their home territory where it hurts.
Yeah.
Okay.
I'm planning on calling it Charge of Light Brigade, but other than that.
As long as you're having fun with it.
Yeah.
Cool. Innocent.
I am also halfway through. I've implemented Negamax and Alpha Beta, which I'm still debugging. Yeah, but as far as an idea of goes, one of the evaluation functional thing about it is kind of looking at possible legal moves from.
Say that again. Sorry.
So an evaluation functional thing about implementing is look at all successor from where I am and add their possible legal moves and then subtract mine from my opponent.
So something like this, minimize opponent moves. So you want your opponent to have as few moves as possible and for you to have as many moves as possible.
Yeah.
Okay. And so keep in mind, when you're building these evaluation functions, and this is very similar to something we thought about on the last assignment, don't try to do search inside your evaluation function. So don't, within your evaluation function, generate a bunch of successors and try to see what's happening. Focus on the board in front of you. So when we think about the minimizing opponent moves, you don't really have to worry about generating successors. Instead, you can just count. You can just generate the list of legal moves for each player and then just subtract the lengths, right? You don't have to sort of do a full-blown, well, I'm going to do a search and I'm going to do this stuff. I'm going to look at everything on every possible future board. And the reason I'm emphasizing this is that's the search algorithm's job, okay? And I've mentioned this to several of you in office hours, but I really want to emphasize it. What we're doing here is decoupling distinct concerns. So even though this is an AI class, we wind up hitting software architecture issues, software design issues. And a lot of why we're going to hit this stuff a lot, even in this class, is much of what we're doing in this class is a lot of experimentation and trying different combinations of ideas. And so to do that effectively, we want to separate concerns in terms of the software design itself so that we can vary different ideas independently and assess their impact in a principled way. So things we've talked about in other courses about using polymorphism to separate concerns and all of that stuff winds up applying even here. Does that make sense? All right, Dan, what are some thoughts you have?
I've implemented Negamax. I've kind of implemented Alpha Beta. I think I've got it implemented, but I'm not convinced I've implemented it correctly. Because it plays good when I go 4 deep. When I go 5 and 6 deep, it plays worse than it did at 4, and so I think I've got something messed up.
That does smell bad, yeah.
And then in terms of other ideas, I wanted to have it do 2 things, really. I wanted to try and give extra weight to kings so that it considers a king more valuable than just a normal piece. I tried just doubling the value, and that's horrible. It just gets trounced. So it needs to be less than twice as valuable as another piece, so I'm going to play with some values.
Okay.
And then I also wanted to go through and also have it be smart enough that if it's ahead, to prefer to trade.
Interesting. So let's write that down. Encourage trades if ahead. Okay.
And then in terms of searches, the one where always go one deeper if the last move was a trade,
The search until quiescent.
that seemed feasible to implement, so I was going to go with that one.
Yeah.
And then the other thing I was going to try and do is with the alpha beta to try and do an ordering of
Mhm.
the nodes before
Right.
just doing the alpha beta.
Yeah. Yeah.
I'm not sure what the ordering is going to be, but I figured that seemed like a reasonable.
Right. Yeah. What you can do is you can apply your evaluation function to every successor board. And well, basically what you do is you apply it to the successor boards and then you sort the array based on those values. And that in principle gets you to interesting boards sooner. Good. Yeah, really what you want to do is you want to accelerate, you want to make the alpha beta cutoff happen as early as possible. So you want big alphas early in order to encourage that. Cool. Austin.
So I have just one weird bug going on with Megamax, but besides that, it should be fine.
Uh-huh.
I took a look at your email and I was like, oh yeah, okay, yeah, that was obvious. But something else is weird going on there right now. So, but that should be done pretty soon. And then, as far as thinking about improving the search algorithm, I was kind of interested in the database, the two database ideas. of,
Okay.
like, openings and endgame positions. And I haven't thought too much about the basic evaluations, but I mean, thinking about like emphasizing kings over regular pieces, I mean, it seems like it could, there's some interesting stuff you could do with that.
Right. But it's good to have a king.
Yeah.
And then it's better to have more.
I feel like when I played, that was always what, when I was a kid, that was always what I was trying to do. So there must have been some like intuitive like thing.
There's got to be something going on with the king.
Yeah.
Cool. Kate.
So I've done Megamax and Alpha Beta. In terms of my extra evaluation function, I currently have one that like works. It doesn't work wonderfully, but it like it's better than basic.
Mhm.
And that's like taking the number of pieces of the player plus the number of kings times 0.1 plus the number of legal moves times 0.1. Because if I did any more than that, then it would lose really badly in basic. And I'm not super sure why, but
So this is a really interesting approach, and there's a lot going on that's really worth thinking about. A lot of what you're doing at that point is trying to figure out how do you determine marginal improvements when material is at parity. For kings and legal moves to be helpful, doesn't necessarily require parity of material, but if you are behind on material but ahead on things like moves, what I think your results are saying is be way ahead, right? Right. There's a sense in which if you have a material deficit, the other board features that compensate need to be compensating pretty hard.
so if you only have like one king, but like no other players, and they have like 10 players.
Yeah. I mean, yeah, at that point, you're probably going to lose, is the likely outcome. So I'm not super surprised about that. I find that actually kind of intuitive.
Also, one thing I was wondering with like going forward with the other strategies, I was also interested in like the database of endgame positions.
Mhm.
I was wondering if there's like a good place to find that. Find one that exists.
Maybe you're welcome to look online. Obviously, as always, if you use an existing database, give it credit, in your solution. If you're feeling ambitious, you can try to generate one. I'll talk more about that maybe after we've gone over everything. But there are some approaches one can take to generate both kinds of databases. Eric.
So I implemented everything up to alpha beta, and then I was kind of surprised like how well alpha beta did. Like I could run like hundreds of tests against the random one, and it would never lose like at all.
What kind of depth disparity were you working on?
Maybe like 5 or 6, not even that big.
Yeah.
So, I mean, I guess that's a good thing because it indicates that it is working properly, not.
Yes. Yeah.
But yeah, as far as the like evaluators, I was imagining something either with like kings or something to kind of keep track of how many vulnerable things there are. Because if they're all kind of like bunched together, they can't steal any of your pieces, but you might be able to steal theirs. Or alternatively, if you have a bunch on like kind of outer edge of the board where they can't be captured, that's kind of just inherently stronger.
Yeah. Those are really neat ideas, to think about what kinds of patterns on a positional level lead to difficulty in an assault. And those can be really nice things to think about because in effect what you're doing is seriously compensating for the search that never happens, right? Like if you figure out how to build kind of an impregnable fortress of checkers, you've essentially compensated for all the search necessary to figure out that they aren't capturable within a horizon. So if you can work out a scheme like that that's effective, it can really turbocharge things.
And it also keeps them from like capturing like 10 pieces all in one giant chain.
Yeah.
Which would be a big problem.
Yeah. Yep, definitely. Blake.
So up to right now, I've just implemented Negamax search, and I'm in the process of implementing alpha beta search.
Yep.
As for an improved evaluation function, what I was thinking about is like trying to like close off, like keep your side of the board like closed off as much as possible. So anytime you make a move, you want to do, if you can, you want to do a move that's like all the way on the other side and closest to your side of the board.
Why don't you run that? I was having trouble visualizing that as you spoke. Why don't you run that by
It's
me?
better if I do it with my hands, but like
Okay, go for it. Yeah.
Say you move right here, the next move you want to make is ideally one that's like all the way down here, and like you just do that like really incrementally.
So what you're saying is you're trying to keep your checkers kind of advancing in tandem rather than sending some lone scout out to be bumped off in the night by the enemy's guards.
Right.
I mean, I guess I'm getting a little metaphorical here. Okay, so in general, your strategy is something along the lines of keep pieces together. Something like that. All right. Ryan, what thoughts do you have so far?
So I have only Negamax done, but I'm still having problems with that.
Mhm.
But I can't really pinpoint exactly
Sure.
like the root of the problem.
Yeah.
So I just actually scheduled the problems 6 hours a week.
Excellent,
So
excellent.
anyway, I was thinking about doing something with like an ordering heuristic
Mhm.
or maybe a table, but I'm not really sure about implementation.
Yeah.
But those are like the main two that piqued my interest.
Cool. Yeah, well, we're going to talk about those more today. All right, David.
So I've got everything up to alpha beta.
Mhm.
The quiescence search sounds really interesting. I definitely want to do that, and possibly endgame or transposition, depending on what we learn after this. But for the evaluation function, this is confusing, I apologize, but
Go for it.
essentially, like you weight each square of the checkerboard,
Mhm.
but you don't just weight it based off of, okay, all the edges are good. But you basically go through with some kind of predetermined like kernel that you multiply that individual like board by, depending on whether or not there's like your piece or an opponent's piece, and then if there's an empty space, and so the kernel will be able to determine whether or not you have a possibility of maybe jumping, or there's maybe this square is like something to attack or something like that. I don't know how you would design that, so I'm just
Okay, so let's talk about this. So David's talking about kind of a fun and interesting idea, which is for each square, its position on the board lends it value, but that value is conditional on what do the other squares around it look like. That's this kernel idea. So you can imagine that there's a window around that square, and given a small number of squares, like imagine a 4x4, right? Actually, no. Let's imagine a 2x2. Okay, so we're considering 4 total distinct squares, each of which has 3 distinct possibilities. My checker, other checker, empty. So that gives us 3 to the 4th power possible combinations, right? 3 for each of the 4, which is 81. Now, here's where it gets interesting. It's not unreasonable to have some means of calculating 81 distinct values for each position, you know? So there are a number of ways that one could do that. One way one could do that would be something like the following. Have the thing play a whole bunch of games a whole bunch of times. For each of these possibilities, you can do some counting about how often do I get in that position and then I win at the end of the game? How often do I get in that position and lose at the end of the game? And you can actually come up with an automated rating scheme based on how often that leads to wins or losses or whatever. So that's one way that you could imagine actually creating in an automated way some values for that kind of a kernel, you know. That said, you know, and part of what's interesting about that, right, is it provides a way of thinking about how valuable is the square at different phases of the game, because in different phases of the game, certain combinations are likely to be predominant over others. None of this is to say that the scheme will actually work well. It's just a way of saying, here's a way we could imagine implementing it with reason for believing it might do something worthwhile. Cool. Jake.
I'm up to alpha beta search, and then for evaluators, I was thinking maybe keeping the back row of my checkers there as long as possible until they're forced to make a move, and have the other ones just try their best to get keys.
You know, so the idea here, and this is fairly straightforward to implement, right? You've got some extra bonus that each checker on your side gets for being in the back row. And then, you know, the other 8 of them march off, and like he's saying, his strategy is hoping they become kings, and you keep these other guys in the back to like assault the enemy if they penetrate that first rank. Should be interesting. Caleb.
So like everybody else, I pretty much got Megamax working, and I'm starting to dip my toe in alpha beta. You kind of described what I was trying to attempt to implement. The way I was looking at it was more like a combination of the opening and ending databases. So I guess I was going to have it figure out how to run through a whole bunch of games and have it track every single game or every single board position that led to whether it was victory or loss, and then put it in the database so it was a victory or loss for each individual board position.
Yep.
And then the more it ran, obviously, the more it did.
Cool. All right, Silas.
Okay, so like everybody else, I'm up to alpha beta search. I'm debugging Megamax a little bit, so I got a few problems with it, but almost there. And then for me, I wanted to do the back row and the kings as well, but also I found it interesting, like I said, the trading, preferring trading, because like once you get ahead and you keep trading, you like increase that advantage, I guess. So I thought that was like probably a good way to win a lot.
Yep. So one way you could think about that concept would be, instead of a material difference, you could do a material ratio, right? Because the more pieces you have, you improve your ratio by evenly trading off. And so, I'm not guaranteeing this would work great, but this is kind of a first way of thinking about, that could be a way of kind of getting towards that idea. Cool. Will?
Still working on Megamax search. Kind of some problems implementing it. And in terms of quantification and evaluation, and thinking of one that, back row one. Another that encourages the AI to be aggressive in its gameplay.
Cool. Mitchell.
So I've gotten Megamax, I think it's mostly done in my alpha beta search. But at least compared to the Megamax, they tie about 80% of the time, which is weird, so there's obviously some conflict.
What's the depth discrepancy? So that's part of the issue. Where alpha beta helps you is, if the depths are the same, it should actually do the same thing. What alpha beta lets you do is search deeper with the same number of nodes, or a comparable number of nodes. So that in principle, given a bounded time window, alpha beta will go deeper than Megamax. So yeah, I'd encourage you to try out and see, well, what if I do a 6-ply alpha beta against a 4-ply Megamax, and that kind of a thing.
And I was going to say, my alpha beta, although they're about the same, they always tie it because it spans 3 times less.
Right. Yeah. Exactly.
And for my evaluation functions, I was thinking of trying to make one where it would look to block the opponent from moving, and also there's some priority.
block opponents. So that's an idea we hadn't really discussed yet. Cool. Fish.
Yeah, so I'm still looking at some things in Megamax and it was an interesting problem with that. And for my evaluators, I have one that gives a little bit of preference to kings, as well as the number of pieces. So basically just like adding kings into the idea of the basic one. And also I was looking at like the number of moves, with the idea that like I would want as many moves as possible because I don't want to be forced to make any specific move by my be forced by my opponent. Which, you know, once I get everything working, should actually look interesting because it should actually give a bias almost against putting yourself into a move where you could take someone else.
Right.
So I'm interested to see that.
Right. There's an interesting tension there because of the requirement to capture if a capture is possible. And I think this is part of where, you know, when Kate said she needed to set the weight down really low for the mobility, that's one place it kicks in because the last thing you want to have happen is to like not capture. So yeah, so thinking about those trade-offs can be really, really important. Cool. Well, a lot of you have a lot of really cool ideas here. And so we're going to spend some time talking about some of these, what some underlying principles are like and how you can think about them going forward. So, bless you. So in general, mobility winds up being a really interesting issue. And part of what makes it an issue is more or less exactly what Fish was talking about. Higher mobility implies that you've got more control over what you're doing next in comparison to your opponent. If mobility is low, that can be symptomatic of an opponent's strategy that by constraining your options forces you into bad things. But there's a tension there. And so the first thing I want to talk about is resolving tension between these things. And Kate alluded to this already, but I'm going to talk about it a little bit more abstractly. That is, you can imagine your evaluation function as a polynomial. Now, what do I mean there? When I say a polynomial, what I mean is you've got a series of weights that are each multiplied by different features in the game. So each of these W's is a weight value, and each of the F's is a feature. And so when I say a feature, I'm talking about kind of these ideas we've been kicking around. So, you know, F1 could be the material difference. You can imagine F2 as something like a material ratio. Maybe F3 is doing something with, you know, mobility and so forth. So you can use the scheme of a weighted polynomial to try to put together a solution that incorporates many disparate elements into a single number. Once you've done that, you can do some experimentation with different values of the weights to get a feel for what would work most effectively. As it happens, this formulation of the board evaluation function as this weighted polynomial actually once again goes back to Arthur Samuel and his early checkers experiments. He was kind of hardcore and he took it a step further. He actually came up with a scheme where he would have the players play against each other with different weight values, and for winners he would look at where the weights were big and make those weights bigger. And when they lost, he would decrease the values of the larger weights on those as well. So in effect, a big weight meant that that feature was getting a lot of credit for the victory, and so forth. So it was kind of an interesting scheme, and it was actually the very first known instance of what's called reinforcement learning, which is now a really big topic, and we're going to spend a solid week on it much later in the semester. Not for checkers exactly, but in a different form. But yeah, this idea of the polynomials is actually kind of captivating. I found it sufficiently captivating. I actually did some work on this in my master's thesis, which was a very, very long time ago. But I had some fun experimenting with a different kind of machine learning approach for that, which is a bit too complicated to get into today. But it's all just a way of saying, over time, I wound up thinking really deeply about this idea. There's really a lot that's interesting about it. But it does come back around to, are you actually picking interesting features? You know, do you have something to talk about in terms of what you're looking at on the board? So coming back over here, yeah, you got to do something with kings. Kings are powerful. Maybe implicit things are enough. What do I mean? Kings get more moves. You know, so it could be interesting if you've got a mobility feature, maybe the king feature can have an even lower weight just because a king being worthwhile is going to add a lot to your moves. Or maybe not. You just got to try stuff out. I do think it was interesting that I think Dan, you pointed out that the 2 points for the king was bad. And Kate mentioned, yeah, around 0.1 was about right. So that gives everybody some ideas of some of the levels of weights you might be looking at when you think about kings. You do want to think about them. Kings make the game. Right. All right. Encourage trades up ahead. We talked about that. Databases. So you all might remember, at least depending on who was teaching it, in the when I teach the data structures class, I have this assignment with the hash tables where you have it learn how to play tic-tac-toe by memorizing board positions. So for every position, it maintains like a win-loss count for if you ever got in that position. And over time, and after playing a lot of games, it actually starts to figure out what some good and bad positions are. You can do the same kind of thing to build an opening database. That is, you can make a decision about the number of distinct opening positions that you want to record. What do I mean by an opening position? I mean a configuration of the board in the early phase of the game, right? What do I mean by early phase? Up to you. You could say first 10 moves, for example. So what you can do is you can take your board and turn it into a string and have that be a key in a hash table. So, so you have the system play against itself over and over again. And just see how frequently does entering that position result in a win or a loss. By using a hash table, your representation can be sparse. That is, you don't have to enumerate all of them. You can just maintain records of the positions you actually encounter. You might be wondering, well, how do you represent it as a string? Well, oh, this is kind of funny. Innocent was pointing out this morning that the checkerboard class seems to run afoul of some important ideas from the scalable software class. Like there are these named constants and not enums. And so I had to make a little confession to Innocent, which is that I wrote this program in 2004. And at the time I wrote it, I actually didn't really know about enums in Java. Wow, it was seriously 16 years ago that I wrote the first version of this program. Holy cow. So that's the first time I taught this class. Was when I created this. Yeah, so it's been around a while, and it's got some artifacts of the way I coded back then, among which is, yeah, these little static things. Anyway, what I wanted to show you all is the toString method, which I swear is in here. Never mind. So, what's that? It's in checkers. It really ought to be in the checkerboard class. Oh, never mind. So, I really thought I had a toString method. Do I refer to strings at all? No. Okay. Never mind. So if you're going to take this approach, go ahead and put a toString method into the checkerboard class. just have some canonical way of turning it into a string, and then you can rapidly look it up in the hash table. Hardcore aficionados of this stuff will encode them using what's called a bit board. And bit boards are a lot of fun because what you can do is try to represent all 64 squares of the board as a single integer. So each bit in the integer corresponding to whether some aspect is true or false of the square. So you'd have like a bit board of where all the red is and a bit board of where all the black is. And so with two longs, you can actually represent the whole board. Bit boards are hugely popular in chess. It really facilitates in chess working out things like, what are all the legal moves for my rook again? You know, taking into account that, you know, it's got to capture something. It can't just sort of keep moving past it, that kind of thing. So, but you don't have to do that in order to implement an opening database. But that's a way you can automatically create an opening database. Endgames are a little harder. Common way to do an endgame database is to start with generating all possible positions that are a win. And then from each of those, you generate all possible moves that could have put you there and kind of work backwards from there, rating those positions based on what they lead to. So that turns out to be a bit harder than doing an opening database. What I described for an opening database, I think, is pretty straightforward. The endgame database, that takes some doing. If you find a nice endgame database online, feel free to use it. Again, credit where credit is due. It'll certainly take some effort to bridge it with your own code. And so it's not like doing that is going to be no work. Phrased differently, I would greatly respect the work that one were to undertake to incorporate an existing endgame database. Likewise for opening. Again, just give credit where credit is due. Let's see. Talked about structure and position a bit. You know, you can imagine doing stuff like every square gets a rating based on how good it is to occupy. So edges are good and center is bad, or things like that. Maybe the further down you get is better and better. That kind of a thing. Keeping pieces together, you know, so this is an interesting feature, right, where you can do something like calculate what's the maximum distance between any two pieces on a side, and then, like, you know, subtract it or something, making it a negative weight. You know, so the bigger that distance is, the worse your eval is. You can do stuff like that. We talked about David's suggestion about the kernel window. Maintaining back row, so this is just another variant of the give specific squares a weight idea. So again, pieces just get bonuses by occupying those squares. And we talked about material ratio. For blocking opponent, again, you can try to find certain patterns that if they happen to be in a pattern, that's better. Here's a simple way to do it. You can give a bonus to a checker that, for instance, is backing up two other checkers. What do I mean by that? So if you've got a checker here, and you also have checkers here and here, this guy cannot be captured, right? So you can do stuff like look at those nearby squares and see if they're also occupied by pieces. And if they are, you rate it as a stronger piece. You know, you like being there. Needless to say, there are more ideas here than any of you has time to try. You know, what I really want to encourage you to think about with this assignment is just picking something that's interesting or intuitive to you and seeing how it does. And don't be afraid to do simple things either. You know, we've kicked around a number of ideas, the implementation complexity of which is considerable. If you feel up to that, I am not stopping you. Go for it. You know, have fun with it. If you're feeling a little reticent about that, you know, I definitely encourage you to think about what things can I do that are interesting relative to what I think I can get done in 4 hours of coding or whatever. You know, I'm not looking for you to just sort of kill yourself with complexity here. I just want you to try something that's interesting, and simple is not bad. One thing I hope everybody has seen here is there are an awful lot of interesting, simple ideas that you can try. And I hope you all have a lot of fun with those. Any questions so far about any of this? All right. Well, I feel like I kind of botched the explanation of alpha beta last Thursday, so I'm going to explain it again. So here we go. So alpha represents best move so far. Beta represents what my opponent can hold me to. So both of these ideas play strongly with the idea that what we're doing is a search where adversaries are interacting. That is, you might come up with something brilliant, but your opponent is always trying to stop it. And so what we're doing with alpha and beta is coming up with what's the live window of opportunity that we're looking at in a particular scenario. So there was some confusion about this issue as well. I tried to straighten it out over email, but I'm going to go ahead and talk about it here anyway. -1 for a win, -1 for a loss, 1 for a win is just a convention. There's nothing mathematically essential about it. If you use that convention, you have to scale your evaluation function accordingly. Conversely, if you don't want to bother with that convention, here's another one you can use. Many of you didn't know this existed. It was fun to point it out. Double dot positive infinity is an actual value in Java. And so is double dot negative infinity. And I had a fun conversation with someone to the effect of, if you use double dot negative infinity, you do not have to put a negative sign in front of it. It's already negative for you. You can, of course, do negative double dot positive infinity if you want to. So you have to wonder, well, what is this? What's going on with those values? Floating point values follow an encoding known as the IEEE standard. In the IEEE standard, they actually define several values that are not, in any stretch of the imagination, actual numbers. Infinity is not actually a number, right? It's something that we use when we're working with limits, but in practice, it's not actually a number. So how does it actually manifest? Well, if you give a variable the value of negative infinity, it is less than every other value except negative infinity, to which it would be equal. If you give a value positive infinity, it is greater than every other value. Aficionados of dividing by zero might be intrigued to know that there's even double dot NaN for not a number. So this is kind of funny. If you divide an integer by zero, Java throws an exception. That crashes your program. That's bad news. If you divide a double by 0.0, it does not crash your program. You get a double dot NaN. And the program keeps on trucking. And if you add anything to an NaN, guess what you get? An NaN. It's like this black hole that sucks all meaning and value into it and lets no information out. Yeah. So, and if you multiply it by zero, it's still an NaN. You don't get to like cancel those dividing by zero and multiplying by zero. Sorry. Doesn't work that way.
NaN for zero. Is it 1?
No, it's still NaN.
Okay.
Yeah. Yeah, it destroys everything it comes in contact with. Yeah. But your program still runs. Now, the real lesson here, of course, is just don't divide by zero. But anyway, just for your information, those things are out there. You can use them. I know at least one of you is. Anyway, alpha, best move so far. Beta, what my opponent can hold me to. Why did I bring up infinities? they can be suitable initial values, right, for these. You can set alpha to start off at negative infinity, and it will be less than everything. You can start beta at positive infinity, and it will be greater than everything. And they'll do their jobs. And you can scale to the -1, 1, and that's fine too, especially if you don't want to play around with these things. All right. So that's what alpha and beta are. The heart of the idea is the idea of the alpha-beta cutoff. That is, if alpha is greater than or equal to beta, then you can stop the search. So in other words, if the best move I've come up with is better than what my opponent can hold me to, if I keep looking for better and better moves, they literally don't matter. Why? Because my opponent can hold me to something worse. So that's the underlying intuition about this thing. Now, I'm going to try to build a somewhat better search tree than last time. We'll see how this goes. Okay? So, without further ado, okay, drifting back in. So we have this root node, okay? And we are doing a game tree search. And we have not hit our depth cutoff. So we keep going, and we still have not hit our depth cutoff. And we're doing depth first search, right? And so we keep going down on the left. And we have just hit our depth cutoff. How do I know? I just made it up. But that's where we are. So what I'm going to do is I'm going to assign values that reflect calling the board evaluation function on these nodes. And we're going to see where things go. So this one is going to be a 0.5. So this gets returned. But when it gets returned, we're going to assume no double jumping or anything like that here. So this is going to be a strict alternating negamax. So when this gets returned, it gets negated. So I'm going to annotate the edge with that. Now we come down here and look. And this one is a 0.25. And it gets negated. And so now we ask which of these is bigger. And it turns out negative 0.25 is bigger than negative 0.5. And so that's the value that's living over here at this node. And now it gets negated as it gets returned on up the tree. And now we're up here, and it's ready to descend. And here is the first moment where the alpha-beta concept matters. Because up until now, we've just been using the default values for alpha and beta. Okay? Now, why is that the case? These are leaf nodes. There's no for loop, and there's no moment at which an alpha-beta cutoff can occur. So it just wasn't really relevant here. Up here, now we're at a point where we're looking at another successor and there can be a cutoff. So what does that entail? Right now, alpha is 0.25. That is this value that we got from over here. It happens to be greater than -1. Okay? Beta is still sitting up here at 1. Okay? And that's what it looks like at this node. Now I'm going to do my recursive call. And when I do my recursive call, at that level, I flip them around. So this is an important issue. They exist entirely as parameters. Whatever you do, do not set up alpha and beta as instance variables in your searcher. That will not end well. Okay. So when I do my recursive call, at this node, alpha is suddenly -1 and beta is -0.25. I had to switch them around because I've changed my point of view. See, I had to flip alpha and beta because now the best I can do is, from my opponent's point of view, the thing that I'm being held to. And the thing my opponent is being held to is now the thing my opponent is actually trying to do their best at. And then I have to negate them to reflect the fact that the evaluations need to happen from the opponent's point of view. So now I'm down here. That's my alpha and beta value. I come down here, I hit my depth limit. So I have to run an evaluation. So when I run my evaluation, let's say this is kind of a pathetic little 0.1. So now this comes up here as negative 0.1. Negative 0.1 happens to be bigger than negative 1. So my alpha gets updated to be negative 0.1. Negative 0.1 happens to be greater than negative 0.25. So now is when I do an alpha beta cutoff. That is, this poor node over here remains forever unknown. Now, why is that? Why such a grim fate for that node? See, at this point, from the point of view of this node, he's being held to a negative 0.25. He just learned he can pull off a negative 0.1. That's great. He's thrilled. But since his opponent is holding him to a negative 0.25, he's never even going to be able to do anything with this negative 0.1. Why? Because if that were the move he were to choose, his opponent would have chosen a move that keeps him from ever doing that. So there's no point in continuing to look. See, if I continue to look and I find something that is worse than a 0.1, I'm not going to change alpha. Why? Because it stinks. If I find something that's greater than 0.1, yeah, I can change alpha, but then when I go up another level, my opponent's not changing its beta, right? It can hold me to that. So there's literally no purpose in continuing. And as we found in our discussion, it turns out that if you implement this alpha beta pruning, you wind up tripling or more, or cutting by a half or 2/3 or whatever, the number of nodes that you need to explore to get to a given level. So it turns out in practice, this really helps a lot, even in checkers. Now, if you go beyond checkers to chess, it goes from helping a lot to helping an awful lot, because there are a lot more possible moves on a chessboard. Question, Dan?
If we're going to do this and you do have the possibility to double moves, do you still want to flip your alpha beta and negate them? Or you don't flip them, you don't negate them?
That's correct. Right. Whether you're flipping and negating in any of this business comes right back to this bottom line issue. Whose turn is it? Right? So if my perspective changes, these values need to change. If my perspective does not change, then the values don't change. And so an easy way of checking that is just to see, I've got this board that I'm exploring, and then I've got the successor boards. Is the current player on this top board different than the player on the next board? If it is, you're switching things around. You're negating, you're flipping. If they're the same player, you leave everything alone. Yeah, Mitchell.
What about on the first call? So like if your first move that you can do is a capture move, or if your current player doesn't change, what would you initialize your output?
Oh, they're always initially the -1 and 1. The issue that arises is when you make the recursive call, do you flip them around? And so there's always an unambiguous answer there, because you can just examine who is the current player in each of these two scenarios. And then that lets you move on. Good question. Other questions about this thus far? Yeah.
When you're going to change alpha, like within the alpha beta algorithm itself, do you take the maximum between the current alpha value and the returned value from
Yes.
the previous call?
Right. That's a great question. It highlights the fact that in Negamax, alpha is already there. It's the maximum value. What you're really adding is beta.
So you change beta or alpha, or you change both?
Well, it's only alpha that you ever change. Beta changes indirectly when we do our swapping around. So it's a real subtlety, actually. But yeah, alpha is just that maximum. So for instance, there was one of you I was working with, not sure who at this point, it really doesn't matter, where we were talking about transitioning the Negamax to alpha beta. And then there was this line in this purported alpha beta, well, my max value is -1. And I was able to say, well, get rid of that line. You don't want a separate max value variable. That's alpha's job. So it leads to some interesting situations where coming in, alpha might already be pretty big, and there's a chance that nothing you look at is going to be better than what you found in another branch of the search tree. And that's okay. Something else I think came up in the same conversation was, again, don't really remember who, it doesn't matter. But there was some confusion about how can you change a parameter value, right? So the thing to remember about parameter values is parameter values are simply local variables that got initialized when the function was called. So no matter what function I'm writing, so let me just throw together a simple function to illustrate the principle, So if I create some function f that has a variable x, and inside it I say x equals x times 2 return x. If I call f of 5, I mean, this returns 10, but it doesn't do anything to that 5. What do I mean? The value at the function call gets copied over to the variable that corresponds to that parameter. So that value is just copied over. So you can change it inside here all you want. It's not going to affect anything out here. Similarly, right, if instead of this, I were to say, n equals 5, f of n, I would get a 10, but if I were to print n, it's still 5. That mostly works. I mean, there's an exception to this, which is kind of scary, right? Which is if you pass an object as a parameter, and that object has a method that lets you change its state, then yeah, that state change is going to be visible after the function call. So what does that imply? Well, it implies that you can't always know everything that's changing your objects. Is that scary? It should be. That's the appeal of the Rust programming language and the Haskell programming language. Those are languages where it's actually not possible to do that, and you can actually have confidence that what your function is doing is everything possible to it. So there's some languages in some of our other courses that actually address that issue, which is kind of fun. Neither here nor there. The important thing is to recognize that you can treat a parameter as a local variable, and it'll just behave that way. And I wanted to make sure everybody was clear on that because I knew that point was confusing in office hours. So, cool. Other questions thus far? Yeah, Kate.
Talk about transposition tables. Are those similar to
Oh, thanks for bringing it up. Yeah, I had neglected that. Let's talk about transposition tables. They basically are very similar, but it's useful to be clear about what a transposition table is doing. So a transposition table, the goal is to calculate a board eval exactly once. So the observation that motivates a transposition table is to say running a board evaluation function can be an expensive operation, especially if there are a bunch of features and you're kind of going back over the board and doing a bunch of stuff. Wouldn't it be cheaper to first see if you've seen that position already? And an important motivating insight here is that this is actually an extremely frequent issue in a search. Now, what makes it a frequent issue? Well, it's the fact that I can make some move, my opponent makes some other move, and then I make a third move, and I could have gotten to that same board with a different order of moves, right? So if you imagine in the opening position of the game, well, let's not just imagine, let me play it out. Come here, checkers. So let me show you all exactly an example of this. So I can move here, my opponent can move here, and then I move here. And notice that I would have gotten into the same position if I had moved this checker first and this checker second. So if you look at it this way, the search tree is actually a search-directed acyclic graph. Right? Because I can converge onto the same interior nodes in the search. Now, by default, what we're doing is we're just pretending it's a tree. Why? Oops. Oh, there we go. Why pretend that it's a tree? Because the algorithm's simpler, right? It's a tree that just happens to have some of the exact same node appearing over and over again, right? But with a transposition table, we take advantage of the fact that its actual structure is a graph. So how do we do that? Well, when we call negamax on some board, the first thing we do is we say if some transposition table that contains my board, then I just return table.get board. In other words, I set up a hash table that is designed to use my checkerboards as a key. And for the values in the hash table, I have the value that I found for that board when I last called the evaluation function. So whenever you call your evaluation function, you don't just return it, you actually take the value, store it in the transposition table, and then return it. Similarly, instead of just calling the evaluation function, or rather, let me back up. It's not only when you call the evaluation function that you can do this, right? This is interrupting any negamax search. So before any return from your negamax function, whether it be the result of traversing all of these possible future boards or what have you, you're actually going to take that value and put it in the transposition table. Because it's not only running the board evaluation function that's expensive, it's also doing a depth-4 search from a given board position. So anytime you hit that again, you just look in the transposition table and you've saved yourself doing some search. Yes?
It sounds like this help in increasing the efficiency of runtime.
Mm-hmm.
Does it help in making better moves as far as the artificial intelligence goes?
Oh, right. Much like alpha beta search, this does not make better moves. What it does is it reduces the number of nodes you have to expand, which means given a time window, you can do more searching. And that's a really insightful point. Some of what we're looking at is about making better moves. Other things we're looking at is about ignoring stuff and avoiding computations we don't need so that we can do other computations with a fixed time window. And that's really what we're going for. And that distinction is really, really crucial when you're thinking about this stuff. Does that answer your question about the transposition tables?
Yeah.
Cool. Other questions thus far? Yeah.
Would you also again iterate a little bit more on the idea used in our data structures class to make the tic-tac-toe more smart by sort of computing all the results and sort of looking them back.
Right, yeah.
Yeah.
So, so what we have is actually a simple, table-driven learning algorithm. We're actually going to start our next unit that we'll be starting a week from today will be our first foray into machine learning, and we're going to see stuff along these lines at that point. But here's the basic idea. Again, you've got some kind of a hash table. They just seem to pop up everywhere, don't they? These hash tables. Yes.
Is there a way to does like the checkers class have like a hashing function in it?
You are welcome to create one. Yeah. I sadly didn't put one in.
I feel like that'd be more efficient than like saving like the string of the board.
Yeah, you can absolutely just write your own hash code. Yeah. Actually, that would probably be really easy to do because you could just treat each cell as a base 3 number. And then let me sketch that out for you all. So before we come back to that. So hashing a checkerboard, right? Each space contains one of 3 values. It's red, it's black, or it's empty, right? So what you can do is, encode these as 0, 1, and 2, say. And so then for the very first square, and let me show you something that's important about this. If you look at the checkerboard class, the board itself is just a one-dimensional array here. And basically there's methods that take X, Y coordinates and figure out which dimension of that you need. But the point here is calculating a hash code, you can just treat it as that one-dimensional array. So, so the first cell is a 2, a 1, or a 0. And then you add to that 3 times the next cell, which is going to be a 2, 1, or 0. And then 9 times the next cell, which will be a 2, 1, or 0, and so forth, right? And what this does is it ensures that every position corresponds to your unique integer value. And so that gets you a nice hash code for the checkerboard. Yeah, Eric.
Would that necessarily fit inside of the necessary bound?
So that's a great question. And the answer is, to some degree, we don't care. So what Eric is getting at is, what if you have integer overflow as a result of this, which is highly possible. If you do, in the end, we don't really care, because if our numbers get big enough that we get integer overflow, then we were going to be hitting those with mod anyway when it got into the hash table. So no big deal. Yeah, those cells are destined to be collisions in the hash table anyway. But it's a great question. Yeah. And that's basically how you can create a hash code. Yeah.
No, I'm worried about that. Is there like a way?
Well, it's fine because the hash table itself kind of handles those collision gracefully. They're gonna necessarily happen, because if you have 64 positions on the thing, 3 to the 64 is way bigger than 2 to the 64. So you couldn't even fit it inside a long, and it.
Right.
So,
It's actually only 32 slots, but your logic is totally.
Well, yeah, only 32 kind of values.
Yeah.
But then, yeah, it doesn't really mess stuff up. I think it'll still count the ones that are kind of toward the end of the board, because 3 and 2 are offset enough that it's not like.
Exactly. Yeah.
Also, would you suggest having cache, having another file in your project directory that has all this stuff, or is this something that you do just within your search?
You would typically do it within your search.
Okay.
For a transposition table.
Okay.
For an opening database, you would need an auxiliary file.
Okay.
Yeah. For a transposition table, typically you destroy the transposition table after every call to Negamax. So on a new call to Negamax, you would have your transposition table that you would have as an instance variable. And but then you would probably destroy it. And let's see. Maybe you wouldn't.
Yeah, what would you want to?
No, you wouldn't destroy it. Yeah, because if they're valid, they're valid. Yeah. You could just keep it around. It would presumably get better as the game went on. Yeah. So the reason you might destroy it is like after a while, it's going to continue to store positions that aren't reachable anymore because pieces have been captured.
Yeah, I guess that's why I was thinking about like caching it, like just within
Yeah.
checkers, is because like if you move, like I mean, which I guess is what the opening database basically is.
Right.
Okay. So
Yeah.
the difference between the transposition table and the opening database is basically the transposition table only for like.
Within the scope of a given game.
Okay.
And a lot of it just is about managing size, right? So in effect, and this is kind of what Innocent was asking about, this idea of machine learning here is basically maintain a giant transposition table of everything you've ever played. Thinking in terms of an opening database as a way of keeping the size down. To say, well, if we're only going to permanently store the boards we encounter in the first 10 moves, it might be more manageable as a file size than if you go through the end of the whole game. And the idea of the opening database as well comes into thinking about having enough plays through that position so that you've actually got something to say. That is, really deep, late in the game, there are positions you might just not encounter often enough to have meaningful data. But in the opening, you're likely to hit lots of positions really frequently. And at that point, you can actually say something meaningful. Yes?
Would it make sense to store this thing? Would it be like a static variable in the heuristic? Or?
I mean, it could just be an instance variable in either the heuristic or in the searcher. Probably the searcher is better because then you can use the table to avoid searching. Yeah, I'd probably put it in the searcher. Yeah, that would be a better place to put it. And then kind of what Kate was getting at about caching, you can either refresh it when the program starts, like the very first time the search, well, when one way to do it is the very first time the searcher ever gets called, it opens the file, loads up the table, just checks to see is my table empty. So it's sort of being lazy for Haskell aficionados. It doesn't return any values until you ask for them. So the first time you ask for something from it, it sees the table is empty. It says, oh, is my file out there? And if the file's out there, it opens it up, stuffs the table full. The very first move, you're just like, why is it taking so long? But then it populates it and it's good to go. Yeah, it's interesting how all of these things wind up being kind of the same idea in a number of different disguises, right? And a lot of it is, to what degree do you want it to help with a particular role as you're thinking about the search? Transposition table is about saying the search tree is really a graph and we don't want to search where we don't have to. Opening database and this tic-tac-toe learning thing, really, you can think of the tic-tac-toe learner as like an opening database, except tic-tac-toe is all openings because it's such a short horizon game. Everything's an opening. Is about saying, offline, I want to have accumulated enough information so that my player is better. But in all cases, what you're doing is for a given position, you're just counting how often was this good, how often was it bad. And what that then in turn lets you do is use that value actually as something of an evaluation number. So it's board evaluation as a bottom-up emergent phenomenon as opposed to a top-down, I'm going to impart information into this. So why does this tend to be limited to openings? In practice for something like this, it's because there are just too many positions to store. Right? And so using an opening database is a way of having a nice trade-off between those alternatives. If you're really feeling algorithmic-y, you can think of this stuff as basically like a dynamic programming algorithm. Yeah, computer science doesn't really have that many ideas, but it has a lot of contexts. And each context gives you a new way of seeing that idea. Phrased differently, throughout computing, you have this constant battle of space versus time. That is, it's often the case that if you use more space, you can use less time. Or if you're short on space, you can use more time in exchange for the space. Modern machines, well, they tend to have a lot of space now, don't they? Time, it's hard to get more of that. Like, really hard. So if we can use up a lot of space to make things run faster, that tends to be the bias that systems tend to have at this stage in the history of computing. We're going to be hitting this idea over and over again this semester, by the way. Space and time. Yeah?
Just on the checkers, GUI, what's the difference between the evaluate board and evaluate with search?
Oh, okay. Evaluate board tells you the board evaluation function's opinion of the board position. Evaluate search will call your search algorithm with the given depth limit and tell you what it evaluates it as given that search algorithm. So this stuff can be really helpful when you're debugging, because if you feel like your searcher is misbehaving, what you can do is just put together a board position, and you might say, this really ought to be positive. And if it gives you a negative result, you know you've got something mixed up. Yeah. So that's why it's there, is to help you debug your board evaluation. Help you debug both the board evaluation and the search. Yeah, innocent.
Would you maybe demonstrate with like this algorithm?
Sure.
See how that would work?
Well, of course, this is the handout version without an actual search algorithm. So it's actually pretty useless. But yeah, you should totally try it out. Yeah. Right. If I evaluate it, it's going to be a 0. And no matter what I do, it's always going to be a 0. Why? Because I'm running no preference. And if I search using no preference, it's always going to be a 0. Because that's all it can do. Because it's really not that sharp. Yeah. Cool. Any other questions? Have fun with this stuff. I'm really looking forward to seeing what you come up with Thursday. Oh, I'll mention Dr. Yorgi gave me a script for automatically putting students in pairs. And so I ran the script and I emailed you all who your partner is. So you can check that and find that person as you leave today and touch base about how you're going to combine your presentations. 15 of the 18 people in the class are here today. 3 are not. So there we are.